Matt Schuler, did you see I sent you an email back that says there was nothing inside that Google file you sent me?
Oh, okay.
Could you check?
I'm going to send you something else then.
Okay.
Hey, where is this Zoom link at?
That's on the agenda.
All right, I should have just sent you something for the models.
Okay, thanks.
All right, I think I added him.
Before we get going here in a minute, I think is Matt W here? Matt W. Thought I'd let him in, but maybe not. Robert, is Robert here? No, guess not. Okay. I think Brendan, you're here though, right? Brendan, Spencer, Ben. I didn't get an email from you for your lab, so I need that from you.
I'll send it.
Thank you. And Matt, I still haven't. Oh, wait a second. There, I think I got it now. Okay. Yep, I got it. All right. Thank you, Matt. And let's see here. Matt Gilman, Josh Riley, I don't think I got an email from you as well for your models for your lab.
I'll share it with you now.
Okay. And then Matt W and Robert, I didn't get a link for your lab, the models. So right now, I'm still waiting for models from a few students. So I'm going to give them a few minutes to get ready. So we're probably not going to get started until about 1:10 or so. So if you want to go get yourself something to drink, something to eat, come back. But I'm still waiting for Matt W and Robert's mathematical and graphical models for the lab. And I think Brendan, Spencer's, and Ben's, I think. Oh, and then Matt Gilman, Josh, and Riley. I think I'm looking for yours too. So how's everybody doing? Surviving? Yeah. I'm glad everybody is. Does anybody know anybody has coronavirus? No?
Toby, do you?
I'm glad everybody's safe then. Okay, Brendan, I got yours. Thank you very much. Josh Greener. Okay, got yours. Thank you very much. And Matt Gilman, got yours. Thank you very much. All right, so I think I'm just waiting for Roberts and Matt W. Okay, I'm going to get started here in a second. Robert, if you're still there, I'm going to go ahead and kick you out until I get your files. You or Matt W. All right, so. Okay, so before I get started, I just want to let you know that the attendance SWIC that comes in after this, again, it's going to be over what we're whiteboarding here. It's going to be the models you see. It shouldn't be that difficult. That's also going to require a code, which is my code. There it is. And I have it in there already, but since I need to remove some people until I get their models anyway from the SWIC, I can't let you access it until probably around, I'd say 2:30 or so, but it should be pretty fast. And I'll send you an email reminder if you forget to do it or whatever. Okay, so I'm going to go ahead and get started then. And I think I'm just going to share my screen with you since everybody shared their files. I think it'd just be easier that way. All right, so. Okay. All right, so let me go to, sorry. Okay, so from last week, we had this demo I kind of showed you where I just had a wire, and we were thinking, hey, if you use a compass near a wire, you can kind of see if there's a flow in the wire. And so I kind of had the idea, well, I kind of wonder, since a compass acts like a magnet, I wonder what would happen if I had a really strong magnet near the wire. And I think we saw that, oh, the wire kind of moved. And so there must be a force that's acting on it. And so I kind of wanted to figure out what are the things that affect that magnetic force. And so students said, well, maybe the amount of flow in the wire. Some students said, well, maybe if you made the magnetic field bigger, maybe there'd be more of a force. And one more thing that was a little bit more difficult, is really kind of hard to show you the demonstration on computer here, is the length of the wire might affect it as well. And so that's what you were kind of doing in the experiment. And it was kind of important that you work with your group here to have lots of variability. Figuring out exactly what the relationships were so that we can kind of, so not everybody's getting the exact same data from this video. So that's why we kind of split it up. Okay, so we had all the groups respond except we're still waiting for one group, maybe. I don't know. So at least we'll be able to get consensus for most of us, I think. All right, so I'm going to kind of share what the models were from each of the groups. And let's see, I think I'm just going to go through whichever one I got first. So this was Kylan's group. And for this one, we're probably, I think if I remember right, is we're going to look at all the models at the same time, okay? So whoa, wait a second, we're missing a model. Kylan, did you have a model there for, this is the magnetic forces versus length?
My apologies. Matt had the data down. That was his
Oh,
model. We just don't have a graph in there, so
all right,
I can
okay.
graph it really quick.
All right, and then how about, yeah, do that and tell us what kind of relationship it is.
Okay.
For the magnetic force versus the flow, it looks like it's a direct relationship. For the magnetic force versus the magnetic field, it kind of looked like it was a top opening relationship. Okay, so that's that group. And now let's look at the next group. Let's see. Atom. The two atoms. They had a direct relationship for the current, a direct relationship for the length, and a direct relationship for the magnetic field. And actually, they didn't actually have a direct relationship for the length. There looked like there was a y-intercept there. Can one of the atoms tell me what percent was that 0.06? If they figured it out, I'm not sure if they figured it out. So let's talk about what that means while they're figuring that out. That means as the length of the wire would go to 0, there would still be some kind of magnetic force. I think that really should be Tesla there, or excuse me, Newton's there. So I'm thinking that doesn't really make sense logically, but they kept it there to be honest because it's not under 5%. I'm just kind of curious what percent it was. For the other ones, it kind of makes sense that it would be a direct relationship once it's linearized, because when the flow goes to 0, the magnetic force goes to 0. We kind of saw that in the demo. And when the magnetic field, the B goes to 0, the magnetic force goes to 0. And we saw that too. It only had a reaction when we have a magnet near it. So the difference with Kylan's is that they had a top opening squared. So I totally understand that because we're trying to get a better correlation. This correlation here is much better. It's 0.998. But look at the y-intercept. We could not drop it off. It was 26%. So Kylan, I see you there. Did you happen to figure out what the model was for the force versus length?
I'm working on it. We have one data point that is super weird, so
okay, got
I'm
it.
just gonna go back and check it really quick.
Did Miranda do this last one?
Yes.
Okay, Miranda, is it possible you could talk?
Oh, there we go.
Miranda, for this one here, I see that you're totally being honest here, that, and I appreciate that the correlation is 0.998, which is much better. But the y-intercept, I'm a little bit worried because it would make sense that when the B field would go to 0, the force would go to 0. And that y-intercept that's pretty statistically significant. It's 26%. I'm just curious, if you force this first one to be linear, which it clearly isn't, but if you force it to be linear, could you drop off the y-intercept? And if you could not, what percent would that y-intercept be? Did you happen to do that, or could you do that maybe?
Yeah, I totally could drop it off.
Oh, you could? Ah, okay, so that kind of makes me think that maybe it might be linear then right off the bat, because that would make sense that the B field would go to 0, that the force would go to 0. Okay, so I think we have actually a lot of agreement between these two groups here. All right, so then the next one, get out of here. This next one, let's see, Kayla's. And they had a direct relationship for the first one. So as the current would go to 0, the force goes to 0. They had a linear relationship for the second one, kind of like the second group did. But again, I'm thinking that when the length would go to 0, it would make sense that the force would go to 0 because the wire would be non-existent. But they're being honest there. They're saying they can't drop it. I am kind of curious if Michaela, what percent was that 0.0392?
It was 10%.
How much was it? I'm sorry.
10%.
10%. Okay. So, I mean, that might just be trying to look at the video and trying to figure out what the force is. Okay. And then for this last one, again, it kind of looked, oh, this one actually doesn't look like a top opening. It looks like a side opening. But again, notice we have this y-intercept. What percent was this y-intercept here? Do we happen to know that, Kenzie? Or was that Michaela?
I didn't do that one. Michaela did that one.
Can Michaela respond? You might have to unmute yourself.
It was like exactly 100%.
Whoa, the y-intercept was 100%. Okay, yeah. So maybe if you could look at your first one and force it to be linear right off the bat, and just see if you're able to drop off the y-intercept, and if not, how close is it to being able to drop off? So just check that out. All right, so very good. I think we have a lot of agreement here so far. Let me go on to the next group. Kobe and Taylor, I think. Okay, so they said for this first one, it's a direct relationship. For the next one, they also had a direct relationship for the length. And for the last one, they said it was side opening. And for this side opening, they were able to drop off the y-intercept though. So Kobe, did you do that one or did Taylor do that one?
I did that one.
Okay, so Taylor, you were able to drop off the y-intercept, right?
Yeah, it was like 4.8% or something.
Oh, that's pretty good. Okay.
Yeah.
All right. Okay. All right. Then I don't really have any questions then, because it definitely looks like a side opening. All right.
Yeah.
Okay. So far right now, it kind of looks like everybody agrees that force versus current is a direct relationship. Force versus length looks like it's probably going to be a direct relationship. And so far right now, we kind of have mostly a direct relationship for force versus B field, but maybe side opening, this last one anyway. Okay, then let's go back to email. Matt Schuler's. Okay, so we have a direct relationship for versus flow, current. For the B field, it looks like it's a, wait, versus length, I think, right? Isn't it length? I don't know, can I edit here or not? I think this would be, the units for the slope here would be, let's see, it'd be newtons over meters. And I think the X here would have been length. Okay, so it looks like they had a linear relationship. So Matt, I'm not sure if you did this one. If you did, what percent was that y-intercept? Oh, that was Kevin.
I did that one. It was about 10%.
10%, okay. So again, maybe that's just reading the scale. Okay, so maybe it looks like, kind of makes sense that it might be a direct relationship. For this group, they also had a top opening relationship. So kind of like I think the first whiteboards that we saw. But again, notice they have a y-intercept here that's 0.148. I'm not sure, Kevin, if you did this one or somebody else did this one. Do you remember what percent that y-intercept was?
About 20%.
20%, okay. Could you try to go ahead and make this first one, pretend that it is linear, see what the y-intercept is, see if you could have dropped it or, you know, what percent it would be, okay? And we'll come back. All right, so, Brendan. Sorry, it's taking a while. I'm trying to do similar to what we do in class. Okay, so it looks like they have a direct relationship for the flow. They had a direct relationship for the length. And it looks like a direct relationship for the B field, but they don't have a mathematical equation there. So who was it? Was this Matt? No, this is Brendan. Brendan, for that.
I'm redoing this one because I found an error that I think is messing it up.
Oh, okay. But the other two are okay?
Yeah, the other two are fine.
Okay. All right, we'll move on. Josh. Okay, so for the flow versus the current, they had a side opening relationship, but they had a y-intercept that they could not drop off. I'm curious there. I'm not sure if Josh did this one or somebody else. Could somebody tell me? Could you tell me what percent your y-intercept was there?
I think it was about 29%.
29%. Matt, could you go ahead and try to force it to be linear right off the bat and see if you could have dropped off the y-intercept, or if you couldn't, find the percent, okay?
I did that already.
Oh, you did that.
I think I got like a 10% y-intercept.
Okay. So I totally understand your correlation is better, but I think maybe we should go ahead and say it's a linear, actually a direct relationship right off the bat, because that 10%, that might be just simply reading the force. That could have been what that was. For the next one, it looks like they had a linear relationship, actually direct relationship, excuse me. And for the last one, they had a top opening relationship, but again, notice they had, whoa, that's a big y-intercept. That seems big. Okay, anyway. So whoever did that one, if you could go ahead and force it to try it out as a direct relationship, find the y-intercept, see if you could have dropped it, or see if it's a better percent anyway.
I can't drop it, but it's a lot better percent.
Okay, let's go ahead and say then it's direct. Okay. All right, then let's see the next group. Wait, I already seen that. Okay, I think that's all the groups. Is there any groups that I skipped? So it looks to me as though most everybody said that the first relationship of force versus the flow is a direct relationship. It also looks to me like we're kind of in agreement that it probably should be a direct relationship for the first versus length. The one is a little bit ambiguous is the force versus the B field. But if you go back through and look, we had probably equal numbers of groups that said it was side opening compared to top opening. And we had a few groups that did say it was direct right off the bat. So I think we ought to go ahead and just simply say it's direct right off the bat, okay? So we have three direct relationships, the force versus the current, force versus the length, and force versus the B field. So if you didn't get direct relationships, could you go ahead and back and look at your data and force it to be direct? Because we're going to have to figure out what the coefficient is, the constant is. So I'm going to give you a couple minutes to do that while I set up something here, okay? Yeah, I want to let you guys know I've been thinking about you guys a lot. I think it really stinks what's happening in your senior year. That's pretty stinky. I'm sure you guys will be fine. It's probably not a big deal to you, but I just don't think it's right. It's not fair. What are they going to do with? I mean, I didn't really listen to Mr. Ginder's announcement to students. Are they going to like have a virtual prom or something? I mean, I don't know.
I think they're considering it, but they said they haven't made any decisions yet.
Hmm.
Oh, dang it.
Okay, so these are the three relationships we have. I put slope 1, slope 2, and slope 3 just as a generic. For you, you're going to use your actual slopes, okay? So, of course, when you're making your own lab response, you'll want to put down what your constants were, which that should be kind of easy, I think. But now what I want to do is I want to come up with a joint consensus model. So the joint model, if you look at this, we have this magnetic force on the left-hand side for each one of these. And you can see on the right that it's directly proportional to the flow, the current. It's also directly proportional to the length, and it's directly proportional to the B field. I'm going to write this a little bit different. I'm going to put the B first just because I think it's easier to remember the equation in a second. You'll see why, or I think it is anyway. But there could be some constant proportionality out here. I'm going to put K. So K times this BIL. And what we need to do next is we need to figure out what the K is. So we've got three equations up there that each of them equal to this equation, Kill Bill. So that means that in that first equation, slope 1 must be equal to, well, let's see, I see the I, but I don't see the B and the L or the K. So it must be equal to K times B times L, which means you could solve for K, and K would be equal to slope 1 divided by the product of B times L. Those were your constants. And you could do that for the other ones as well. And what I would like you to do is find each of your K values. Hopefully they'll be the same. If they are, then go ahead and average them. If they're not, then find hopefully two of them that are pretty close to the same and average those, okay? So I'll go ahead and finish these up to help you out. Slope 2 equals, let's see. Okay, has anybody got a K value I can write down? So just shout it out whenever you get a K value. You might have to turn on your mic.
0.47.
0.47, okay.
.497.
Say it again, sorry.
0.4 0.97.
Okay, thanks.
I got 0.481.
Thank you. Again, just shout them out when you get them.
I got 0.7.
Thank you.
I got 0.665.
Thank you.
0.53.
Thank you.
I got 0.60.
Is that everybody? Did I forget anybody? Joe, did I get something from your group? Did I get a number?
I'm in Joe's group.
Oh, that's right. Okay, thanks.
No, I thought Mark said
Yeah,
Yeah,
all right.
no,
497.
Okay. Josh O'Reilly, did I get from your group? Yeah, okay. I'm assuming unless I hear. All right, can we go ahead and average those numbers? What do you get when you average them?
It's 0.56.
0.56, okay, 0.56. All right, so it's not too bad, considering we're not actually doing it in the room. We're doing it on a video. That's pretty good. The accepted value we're gonna say is 1, so it's a little bit off, but it's not too bad. So the accepted value, we're gonna say the accepted model is going to be k, where k is equal to 1, so 1 times this. I actually need to go a little bit further than that. So hold on a second while I see if I can pull up. There's some questions on the backside that show this right here. Sorry about that. They show this magnet here with this wire. This wire that's kind of carrying a current through it. And I want you to notice here, in fact, I'm going to go ahead and draw in the magnetic field that points from the north toward the south and I'm going to make it red. Parents are so much fun. That's all right. I'll embarrass her with the video afterwards. Okay, so yeah, she thinks I don't work. Okay, so here we have this magnetic field that's pointing from the North Pole to the South Pole, and we have the current we can see going into the page like this. I want you to understand that that wire doesn't necessarily have to be exactly like that. It could be, in fact, it might have been sort of like, in other words, maybe it doesn't look like this exactly. It could have been at an angle a little bit. So it's twisted a little bit. And so that might be one of the reasons why we didn't get exactly one. So no fault of your own whatsoever. But this kind of brings up something here that's kind of important. And that is that this force that's exerted on the wire acts in a certain direction. It doesn't actually work very well when I showed it to you as a demo. It's kind of hard to see three-dimensionally on a flat screen. But with this picture here, the way I have it, in fact, let's go back to this one here. The way I have it on here, this would actually have a, let's see. This would actually have a force on it, the X downward. And I need to show you how this works. It's using the right-hand rule, but it's a different right-hand rule. If you remember, we already have a right-hand rule for grabbing. Remember where you grab the wire and you figure out the direction of the magnetic field? That's a different rule. That rule helps you figure out the direction of the magnetic field. We don't care about that in this problem because we know the direction of the field. It goes from here to here. What I care about is what is the direction of the force. So this right-hand rule is called the force right-hand rule. So now we have two right-hand rules. The way you use this one, so I'm going to try to model on here, is your thumb points in the direction of the flow. So you see the X there? I'm going to have my thumb point in on the right hand, has to be the right hand, points into the page. My fingers will have to point in the direction of the B field, just like before. But this time the B field is pointing from the north to the south, like that. And now my palm points in the direction of the force. Okay, so my thumb points this way, fingers are pointing from north to south, and there's a force on this wire pushing it downward, like this. Okay, let's try one more. So this is another picture on here. It's the other part of the lab. So for this, you have the flow that's towards you. So my thumb would have to be pointing towards you. My fingers still have to point from north to south. And now my palm is pointing upward. And so there's a force on this wire that's upward. But here's what I want you to get from this is notice which direction the force is compared to the field. So let me go back to this one because it's easier for me to do. So the field points from north to south and the force is downward. What is the direction? What is the angle between that field and that force?
90 degrees.
90 degrees, exactly. Same thing for the other one, but this one's easier for me to do with my hand. I also want you to see the direction, the angle between the force and the flow. So the flow is into the page. Maybe I should do it like this, is into the page, and the force is down. What is that angle? What is that angle? So the flow is into the page and the force is, it's also 90, exactly. So I want to come back to that equation we were looking at a second ago here. This B times I times L, I actually need to include one more thing for this, because if this wire, get the rotated one. If this wire rotates all the way around so that it's pointing, let's say from north to south, so that means of course the magnetic field lines point like this, but imagine if the current was also that way. Guess how much force would be on the wire? Say it loud, I can't hear you. Unmute yourself.
0.
0, that's right. So looking at this equation here, I need some kind of trig equation that has a maximum when it's 90 degrees and a minimum when it's 0 degrees.
Sine.
That's it, sine. So the equation really is BIL sine of theta. Students like to call this Bilson. This equation is Bilson. So class, say hi to Bilson, Bilson, hi to class. You need to understand that that angle, theta, is the angle between the current, go back to this one, is the angle between the current and that B field. So in this case, it's 90 degrees. In this case here, the current is not going to be at 90 degrees to the B field because it's been rotated a little bit. So it's a little bit less than 90. And so that means the force is going to be a little bit less. If it rotates all the way around so that the angle is now 0, there would be no force. So one more thing I think I need to reiterate, I've already said it, but I want you to really understand it. That this force, I'm going to see if I can highlight it there in red. That force is always perpendicular to the B field, always. It's always perpendicular to the B field. It's also always perpendicular to the current. Now that doesn't mean that the current is perpendicular to the B field. That's not necessarily true. So for instance, in this case, the current is not perpendicular to the B field, okay? And of course, the length of the wire, that's always going to be the same direction as, or collinear with the flow. Okay, any questions on that? Okay, so I'm kind of running out of time because I don't want to keep you too long. We might have to extend this over one more day. So let's see, what do we want to do here? Been already on here for 40 minutes. So you know what? I think I'm just going to hang it up there for today. So next Wednesday, we will finish whiteboarding this lab, so you don't have to turn it in yet. You do have to do the SWIC, the attendance SWIC, so I guess I need to go ahead and give you all the digits for this, so if you can copy this down. These are all lowercase letters. Z as in zebra, D as in dog, G, N as in Nancy, Z as in zebra, D as in dog, the number 4, the dollar symbol, and the number 9. So there's 9 digits there. ZDG, NZD, $4.9. Like I said, you're not going to be able to access it until about 2:30 or so because I have to make sure not everybody participated here, so they're not going to get access until I get their stuff. On top of that, since we didn't get through this whole thing, I'm going to have to modify the SWIC a little bit to make it fair. Any questions? So let me go back to the calendar and see exactly what we need to do. Okay, so if you're looking at this, trying to figure out, okay, what do I need to do? I'm going to have to modify some stuff here. Oh, this is from last week, sorry. We whiteboarded, got the mathematical models and stuff. I would like you to finish up the lab response. That way we can hopefully quickly whiteboard it on Wednesday. I think I would like you to also keep on working on the Ampere's Law worksheet. I think we started it, I think. We'll also work on that. I doubt that we'll get to the next worksheet though. So that'll be coming after that. So So, oh, and also, of course, the SWIC then tonight by midnight, and I'll have that ready by 2:30, like I said. Maybe I should give you an update. You guys probably know this already. I posted it over here. I hope that you can kind of see my cursor. The last day of class, this is kind of exciting. Maybe for me more than you, I don't know. But the last day of class is the day of the test. Actually, it's not the day of the test because it doesn't really make sense to have that because I don't want to cause you to panic about the test. It's actually going to be the Friday right before. So your test is on Monday. I think it's like around noon or so. And so there's no final. There's no senior project, which in a way is kind of sad because those are kind of fun actually, but less on your plate. So we've already covered everything. So I hope that you're still doing the internet homework, which I got to put those scores in because I really think you guys should do really well on it, especially since there won't be any of this magnetism stuff on there. So any questions? All right. Thanks for coming. I appreciate it. See you later. Bye.
Bye.